morning. The momentum version of Newton's second law is net force equals the derivative of momentum with respect to time, where both force and momentum are vectors. Bo, please rearrange that equation and take the integral of both sides.
Sure.
Flippin' physics.
Multiply both sides by dt. Take the integral of both sides. The left side is from time initial to time final. The right side is from momentum initial to momentum final. That means we get momentum final minus momentum initial on the right side, which equals change in momentum.
That is impulse. You just derived the equation for impulse.
We already knew the equation for impulse.
But you just derived it, which is cool.
That is correct, Billy. Bo just derived the equation for impulse. Now, the symbol for impulse is a capital J.
Why not capital I?
Capital I is for rotational inertia.
Or moment of inertia.
They are the same thing.
Yeah.
Okay, capital J for impulse.
Okay, please recall that the impulse approximation states that often the force of impact is so much larger than all the other forces acting on the object that we can consider the force of impact to equal the net force. Therefore, according to impulse approximation, we can replace the net force in our impulse equation with the force of impact during the collision. And usually the symbol used for the force of impact during the collision is just capital F. All right, there are many things I need for you to remember about impulse. Impulse is a vector. That means, class, impulse has both
Magnitude and direction.
Correct. Also, I will just reiterate that the symbol for impulse is not capital I. It is capital J. I'm repeating that because students often forget that. Typically, that sounds like this.
Mr. P, what does capital J stand for?
Or this.
Dude, what's capital J?
Or even this.
There's a capital J on the equation sheet. Does capital J stand for joules?
So please remember, the symbol for impulse is
Capital J.
Yep. There are three equivalent expressions impulse is equal to. Class, please tell me all three.
Impulse equals change in momentum.
Impulse equals the integral from time initial to time final of impact force with respect to time.
And the third?
Oh, the area under a force versus time function.
Right, that's the area definition of an integral.
Area under the function where area above the horizontal axis is positive and area under the horizontal axis is negative.
Correct. And Bo, what are the units for impulse?
Well, impulse equals the definite integral of force with respect to time, so newtons times seconds.
And newtons are kilograms times meters per second squared, which means Newton seconds are the same as kilograms times meters per second, which are the units for momentum.
Right. But realize, typically we use Newton seconds for impulse and kilogram meters per second for momentum. It helps delineate the difference between impulse and momentum. Bobby, what is the integral equation for the definition of work?
The integral equation for the definition of work. Well, that's not the dot product of force and displacement. That's for a constant force. It's work equals the definite integral of force with respect to position.
Yes, thank you, Bobby. Please notice how similar this integral equation for work is to the integral equation for impulse. Clearly, they are not the same. However, students often confuse the two.
Work integral equation is with respect to position. Impulse integral equation is with respect to time. Got it, Mr. P.
All right, let's take a look at a typical force as a function of time graph for a collision between this dropped rubber playground ball and this force platform. First, let's watch it at real speed. And now let's watch it at 40 times slower than real speed. And while we wait for that rubber ball to actually collide with the force platform again, let's take a look at the force of impact as a function of time graph. You can see all of the data points create a function roughly in the shape of a concave down parabola. And notice that the total time during the collision is less than 25 thousandths of a second.
25 thousandths of a second is not very long.
25 milliseconds. Whoa.
Yeah.
Remember that the area under this data is the impulse during the collision. Also, remember that the area under the curve can be approximated using a rectangle with a vertical side equal to the average force of impact during the collision, and the horizontal side equal to the change in time during the collision. In other words, impulse also equals average force times change in time. So yeah, there are a lot of equations for impulse. Your job is to keep track of all of them and know when to use which one. To review, impulse during a collision, the symbol for which is a capital J and is a vector, equals change in momentum, which equals the definite integral of force with respect to time, which equals the area under the force versus time function, which equals the average impact force times the change in time during the collision. And that, of course, does not equal work, because work equals the definite integral of force with respect to position, not time. Thank you very much for learning with me today. I enjoyed learning with you.